thank y'all for coming out. I'm Dave Wilson. I was asked to do a session for the Hamfest today, and I talked with Gary Owensby, who was setting it up, and as we went through, I had one thing in mind. He had something a little bit different, so I've kind of tailored some of my work towards that. But today we're really going to talk a little bit about backup power and alternative power sources. This is a very big topic. It can cover a whole lot of stuff. Now let's see if I can get this beast to work. What is backup power? Any ideas? Why do we need backup power? Backup power is another power source. Usually it's not the main source you use. So when your main power source, you need a backup. Now, that backup can be a whole lot of different things depending upon what you're needing it for. Because in thinking about it, we tend to think electrical, but there are lots of other power needs where people have backup power sources. What is an alternate power? What's different between alternate power and backup power? Backup usually is your emergency source. An alternate power is an either or. I can use A or I can use B depending upon what reason I want to. I've got a machine. I can run it off diesel or I can run it off gasoline. Or I can run it off LP gas. What's the cheapest to get the job done today with it? Oh, it's going to cost me $100 diesel. It's going to cost me $150 on gasoline. It's going to cost me $80 on LP. LP wins today. Next month, what do? Oh, diesel's the cheaper instead of LP for whatever reason. So alternate power, that's just a different power source so you can switch around for some reason. Could be economics. You know, cheap gasoline is great. I got a station. They're going to call me the next time they have a tanker load that they'll sell me at 89 cents a gallon. Been waiting for that call for many years. And guys say, oh, I'll get it to you. I'm still waiting for that call. So,
what's LP?
Liquid petroleum. Yeah, bottled gas and all. And so, yeah, LP gas. I'm old timer. I know some of that old stuff. But alternate power, you know, that could be your generator. How many people got a generator at home or whatever for emergency or to drag out whenever you go do a winter field day or summer field day or you're out someplace and you need electricity at your picnic? Well, that could be. It could be fossil fueled. It could be permanent. It doesn't have to be portable, but it could be permanent. If y'all watch ads on TV, Generac loves to do ads about how their power works when the lights go out and how it comes on so quickly. Well, that's an alternative fossil fuel permanent installation because those suckers, they put a pad on and you got there. Temporary portable, that's the 1.5 to 2 kVA generator you pick up and you carry. The new ones all have inverters on them. Can be real good, but they can be electrically noisy for your radio stuff. Wind power. There are people out there selling windmills nowadays that are run to 2 kVA, maybe 3 kVA. You can put them on a pole. Not real popular around here because our winds are so variable. There are places out west, that's what they use, and they don't have a line to the utility because they're so far out. They're not in the sticks because there ain't no sticks. And all, they're out in a desert area with mesquite. There's nothing above 12 feet high except your windmill that you put up, so you've got 3 kilowatts of power. Water powered. As crazy as it sounds, you'd be surprised how much power you can generate with just a little bit of water. So there are, you know, that would be an alternative scheme. Some of the people who are in the prepper community or survivalist community, they're going to be very interested in some of these other things because they are different, because that is another opportunity for them. Some other sources, solar. I can go here, over at the airport, they've got a huge solar farm. I could go over downtown Chattanooga area. EPB has over 1 megawatt of solar power. So these are commercials, but you'll see ads and people wanting to put solar on your house. These are other alternatives because maybe that solar won't do enough to provide power all the time. But if I get some energy storage with it and all of a sudden it starts becoming more viable. EVs. I'll pick on Ford Lightning, because they've made a big deal out of it in some of their ads of recent, to where their truck is the backup power for the house. They've got an inverter in it, and they got some outlets in the back of the bed and whatever. I haven't looked at it, but from what I recall from the ads, and they advertise how they could use the truck to power the house. I don't know how viable that is, but that would be a possibility. Another area that we have is something we have used for years, and that is batteries. The lead-acid battery's been around for a long time. I don't know Voltaic, but Volta and all way goes back. So it goes back a long way with the original battery piles. But then they turned them into the lead-acid battery, which became a viable product. Lithium batteries. Lithiums are pretty new. I'll have a slide later talking about showing how new lithium is. One of the other things we get into, though, is this category called other. Lithiums are new. There's a lot going on in the lithium area, and a lot of people are looking at other batteries. I saw in the past week somebody was doing some research work with a phosphorus-based battery. They're still playing with it in the lab, but they're saying, that looks like that might work. Phosphorus is pretty easy to come by. So it's a plentiful, so they're looking at inexpensive materials to where you can make batteries and all. So there's a lot of research going on. So as you get closer to what I'll call state of the art, you're more likely to find changes, especially with newer technologies. Little trivia. How many people like sports cars? Familiar with a brand called Porsche or Porsche? Depends on how you pronounce it. Guess what their main product was in 1905? What car? It was an electric car. The internal combustion engine had not developed very far at that time. And when it went mainstream, the electric vehicles basically disappeared a little over a century ago. And the battery has been the weak spot in electric vehicles for over a century. So that's why all the work has been going on. If we're going to have a system, how much power do we need? A watt? 100 watts? A kilowatt? A megawatt? Gigawatt? I mean, these are numbers. But how much power do we really need from our systems? What are you going to power with it? I can remember I grew up in a house, our electric service, we had a 60 amp fuse box. We had a main fuse, we had a fuse for the water heater, we had a fuse, I think, for the stove, and we had 4 or 8 screw-in Edison fuses. 60 amps for the whole house. Nowadays, a house with 60 amps, the first thing they're thinking of is, how quickly can I get it changed to something a bit more robust? 125 amp or 200 amp service or more, because, well, that house I grew, when they built it in 1954, they didn't have air conditioning. So, What do you need to power? And you go through that. And how critical is it to have? Well, I'd like to power my air conditioning. Well, do you really need your air conditioning? Some of us remember growing up in houses that didn't have AC. Some of us like to go camping and there is no AC. And I'm talking camping, not glamping, but camping. And because I've yet to see a backpacker carrying an air conditioner. And I don't think you'll find any on the Appalachian Trail with an air conditioner for their tent in their backpack. You know, when it's hot, it's hot. And so, what are your critical loads that you really have to have? And what happens if you don't have these items? If you've got a medical need, or somebody does, and they need an oxygen concentrator, that's definitely a critical item, because what happens if you don't have it might not be desirable. So we need to pay attention to what we call a critical item and why. What makes it critical? And that being critical also has a time window to it. If it's critical, like an oxygen concentrator, that may be, I got to have it all the time. Where that critical, well, I got to have my electric washing machine because I can't wash all my clothes in the creek and all, and I got to have the dryer. Well, maybe you can go a week without that. So, you know, you have to put in that time factor as well. So there are a lot of things that come into this. Can you substitute something else? Like instead of that electric washer, there's a creek here, I could use that if I had to. I mean, there are lots of things that come into mind for these. Can you change what you're doing to accommodate that different? Maybe I don't need to stay up to 3 a.m. every day and sleep till noon. Maybe what I need to do is get up about 6:30 and use all the available sunlight. When it gets dark, bedtime's going to be 9 o'clock or 10 o'clock, not 3 a.m. So there are things that, you know, we can change our lifestyles in order to make some of these unobtainable energy sources obtainable. The backup power and alternate power there, when we go into all these things, I could literally, as I was talking to a couple of people, I could do 8 hours a day for a month and still not have that fully covered. What I want to do is discuss things of a little bit more limited nature with DC power, with radios or other DC equipment, and think about how much energy it needs so that we can go into sizing a battery. So if I'm sizing a battery, one of the big questions is, what power do I need? What is the voltage range my load can accept? If I've got something that I've got to have 24 volts DC for this sucker, my 12 volt battery by itself ain't going to work. I got to have a couple of them. Oh, it's 12 volts. Is it really 12 volts? Will it tolerate 13.8 volts? Will it tolerate 10.8 volts? Those are important numbers, and I'll get to them in a minute on why. How much time do I need to operate? I mentioned time was important a while ago. Oh, we're going to run field day and we're going to run on battery. Okay, that's about 24 hours of operating time. The fault out, New Madrid fault has slipped. We got our big problem, guys. I may be talking days and weeks of needing power, depending upon how much damage and where you are. If you're here, it could affect you. If you're out in Memphis or Dyersburg or that area, well, the last time they had a big fault slip like that, the Mississippi River flowed north for 3 days. Created Reelfoot Lake. So, what's the hazard you're protecting against? How long do you need to run? Because you need to practice for what you're going to be prepared to deal with. I'll pick on a thing last weekend that we were prepared. W4SET just came in. He organized an event where we set up and we ran 2 evenings helping out at Enterprise Nature Park South. Enterprise South Nature Park. That's right. It's ESNP, not ESPN. So he organized that, and we worked out there. But also Saturday morning, we helped the Red Cross with a project, sound the alarm. It's a great training exercise, and I learned a lot from it. But we have to do and practice these things so that in a real emergency situation, we're prepared, So your operating time for whatever, I'd use radio as an example. It doesn't have to be radio. Could be other things like an oxygen concentrator. So whatever we can go.
You were talking about time, the ice storm of 96 or so, 94, 96. My mother was down in North Mississippi. Her house was out of power for 6 weeks.
Okay. Oh, just for you know, we are recording this, and it may be used, so I won't repeat it. So you mentioned your mother's house in North Mississippi was without power for 6 weeks. The good news is power came back. The bad news is it was probably a real tough time for that 6 weeks. I can remember being home where I grew up in eastern North Carolina having an ice storm. Our heat for the house was a fireplace because we had no electricity. And about 5 days or so before we got power back, the lights came on and Mom controlled herself and didn't backhand my older sister when my sister said, "I wish the telephone had rung." But we made do and all. We had a pump out in the yard, so we had water and all. But we made do with what we had. We had firewood, so that, was it the best we'd ever done? No, but we survived it and all. So that was back in about 1967 or so in eastern North Carolina. So what is the current and power needed by the load? We see all these warnings about not overloading drop cords and all. We've just, here in October with fire protection stuff, they talk about not overloading cords, tripping, having frayed cords and stuff. Well, how much current do you really need? So you got to make sure your equipment is capable of providing that current. Because, I need 100 watts. Well, do I need 100 watts at 1 volt, which means 100 amps? Or do I need 100 watts at 100 volts, which is 1 amp? Quite a bit difference in the cable sizes for 1 amp or 100 amps. And that affects your battery stuff too when we get into it. Lead acid battery cells are rough. We think of them as 2 volts per cell. They're actually 2.08 volts per cell at 77 degrees Fahrenheit when they're fully charged. The range, 10.5 volts to 14.4. 14.4, that's pretty high, but that's when you're equalizing a battery and all. You'll get up to that high voltage, but the definition of discharged lead acid battery is 1.75 volts per cell times, in this case, 6 cells, which comes out to be 10.5 volts. So when that battery hits 10.5 volts, it's considered to be fully discharged and all. Float voltage is 13.5 to 13.8. Depends on your batteries. A lot of your batteries that are your flooded batteries, that is, that you open up and you add water to and check the electrolyte levels, they tend to be at the lower end of the range. The upper end of the range are your maintenance-free batteries. They're not maintenance-free, they're maintenance-resistant. They put them together so you can't add water to them, you can't do anything with them. And that, I can't say I created that. That came from Dave Fader, who used to work for Bell Labs many years ago. He said there was no such thing as a maintenance-free battery. They're just maintenance-resistant. You just can't get to them to maintain them. And The old telephone company, they've got batteries that they bought intending the batteries to have a 40-year service life. So, if a load can't accept a wide range because the battery voltage changes, we may have to put other equipment between the load and the battery. Maybe we've got to have an inverter system that'll correct or some kind of power supply system to give me a regulated voltage that'll boost or that'll raise or lower the voltage. Maybe I run it into an inverter that'll give me an AC output that'll take a wide DC input range and give me a nice constant output AC range. Maybe I need to think about a different type battery system. Those are lead acid. Lithium batteries are much different, and we'll get into that a little bit later. Protection time. Why do we have what controls and constrains our protection time? How long do you want to run there? I'm not going to sit at my radio 3 days nonstop, at 72 hours. They're going to be probably looking a hole to plant me in because I won't be able to make 72 hours. So even though I may want a station to run that long, I may not be there. But what are legal requirements? Certain legal systems, like emergency lights, they have prescribed amount of time that those lights have to be at a minimum brightness or greater. So there's some legal requirements, especially on legally required backup systems. I mentioned emergency lighting. Convenience. How long you want it there? It's convenient for it to be able to run for 3 days, but that's what you want because it's convenient, not because you absolutely have to. Budgets. Backup systems can be expensive. So if y'all were in the tower presentation, the guy liked the big tower, but it's kind of like, budgetary constraints may prevent you from having that 16,000-foot tower, assuming you could get the permitting, but, so you have to look at the budgetary constraints and also how much room does it take. You'd be surprised how big battery systems can get when you start talking about long protection times with substantial amounts of power. And when I'm saying substantial, I'm talking about, we need 250 kilowatts for 2 hours. I've been working on a project, and that's the size of the battery that they're going to need. And people are scratching their heads on, because I'm not the designer, I'm reviewing the design. And I went, guys, y'all need to look at your battery space. I don't think your battery is going to be bigger than the space you've allotted. And sure enough, the design, that was very early in the design, and later iterations, they got a lot more battery space for some reason. Some of the loads, we need to consider some of the load requirements. Are they constant resistance, constant current, constant power, or some combination of these? Constant resistance load, that's just like a resistor. As the battery voltage drops, the current will drop. Constant power load, that's a UPS. As the battery DC voltage goes down on it, it starts drawing more current because it's still trying to put out the same number of watts. So that's constant power. Constant current load. Basically, the battery voltage changes, but the load current, it's like somebody painted it on that old analog meter. They just painted the dial, the pointer on the dial, and it stays right there. Voltage goes up, pointer doesn't move, it stays right there. It's constant current. Most loads are kind of a combination of these. Most UPS type batteries are rated in watts. Everything else is rated in ampere hours. They're saying I can draw X number of amps for Y number of hours. But the UPS people, they rate them in watts because they have the problem of as the battery voltage drops, the current goes up. And it's just easier to express it in watts. Not that it can't be done, but it's easier to do for people to understand. I'm going to walk through a sample calculation. I didn't bring a calculator. but this will show you how to do it. And some of these numbers we can change on the fly, but it just won't be on my slide. I'm going to take an example of a radio, Yaesu, a popular radio. They sold a good number of them. It's a nice radio. It could be anybody's radio. It could be an old Tech like the club just sold today. If you put an inverter between the battery and the radio, I can treat it the same way. But I need that radio, 13.8 volt, plus or minus 15%. How am I going to run it? Well, I figure I'm going to be transmitting about 2 hours and listening for about 22. Not serious contesting, not crazy stuff that where I'm, even if you figure, a lot of people heavy duty contesting, they're only going to be transmitting maybe 40% of the time. You got to spend some time listening, either listening for a call sign or as you're exchanging information for your QSO. So I chose 2 hours. We could make it 4 hours or 6 hours. The calculation works essentially the same way. But a problem I have is I don't have all the information I need yet. What kind of information do we think we still need? The current draw while the radio is receiving. We have to estimate it or measure it. I don't have that radio, so I estimated it. I call it 2.3 amps. And even if it's a published number, you got to look at what the manufacturer said the radio was really doing. Did it have all the lights on it? And it had the volume cranked all the way up? Or was it barely a whisper? And the lights were off. That changes the current demand on the radio. So, there's a bunch of assumptions that you have to go into, but you have to make them considered assumptions that make sense and all. So, I estimated that. Now I calculate the ampere hour requirements of the load. But you said we're doing battery. Yeah, but if I don't know what my load is, I don't know what I need for my battery. So, for the ampere hour demand of my load, I've got 2 hours at 23 amps plus 22 hours at 2.3 amps. Multiply it all, and that comes up to be 96.6 ampere hours. Is a 100 ampere hour battery going to do the job for me? I see one going yes. I see one doing this, and I think I see some going, yeah, I don't know, shrugging their shoulders. No, I would say a 100 ampere hour battery is not acceptable. And notice I haven't said a word about what the battery technology is. This is battery technology independent. The battery aging and wear out has not been considered. When the capacity of a battery drops to 80% of its original capacity, at that point, the battery is considered to be worn out. This is not me. This goes back to IEEE standards. International Electrical and Electronics Engineers. It's an industry standard. There are about 600,000 or so members worldwide. They publish lots of standards, and they do a lot of standards related to standby batteries. So this isn't me dictating it. This is a published standard that's internationally recognized, where that comes from. A second question is, what is the environment in? Cold environment is batteries don't like the cold. Some batteries tolerate it better than other batteries. But if you have extreme cold, none of the batteries really like it.
25 years in Michigan and 29 years in Minnesota, batteries run out. Say you buy a 15-year battery or whatever, you're probably getting 5 out of it or something.
I used to work for a battery manufacturing company. They had what we call an outdoor cabinet with large battery cells. The cells were on the order of 150, 200 pounds each. We had a battery heater blanket 1 watt per square inch that set on the bottom, the battery cells set on them to help warm the cells so that when the temperature dropped down to minus 15 Fahrenheit, the battery was more than just a boat anchor or a snow catcher, because usually those are some hostile environments. But you've got to take that into account. If it's a cold environment, battery capacities will drop. Hot environments are not good for the batteries. It'll hurt them, but usually they don't kill capacity, they just kill battery life. What is the minimum battery voltage drop that you can tolerate? If you remember back that Yazoo radio, 13.8 volts plus or minus 15%, that's 11.73 volts. The lead acid battery people rate their batteries on amp hours to go to 10.5 volts. So, I need to correct that. And you have to work with the battery manufacturer's information to determine how much correction you need. So, in this case, I would say 120 ampere, 125 ampere hour battery might be okay, provided that load, that radio would tolerate the lower voltage. Now, by tolerate it, it means it doesn't damage it and it doesn't make it go outside its specifications as far as out-of-band noise or your spurs and stuff. If it drops to 85, from 100 to 85 watts, that's probably going to be acceptable. But if it starts putting all kind of other junk in other parts that you're not supposed to be transmitting, that's not going to be so acceptable. So there are other things that play into it, because maybe I can run that radio on a little lower voltage. It becomes an 85 watt radio, not a 100 watt radio. So here I've used the 1.25 because the 85% or the 80% for the battery wear out, and that puts me to 120.75 ampere hours. Given the accuracy of some of the estimates, 120 ampere hour battery would probably be fine. 125 would be okay. Because I don't think, we're not going to be I'm going to try not to be out in Minnesota winter weather, in a blizzard. But as I say, you need to look at the manufacturer's discharge curve to see what it'll do. I'm already mentioned, how's that load going to respond when you get below that 11.73 volts? A lot of batteries have a limit on charging current. And it varies according to the battery by manufacturer. And even the manufacturer, it may depend on which of the batteries they offer. They offer one battery that may be that'll have a different limit than some other battery. A lot of lead acid batteries, you can recharge them up to about 1/4 of their ampere hour rating. So a 100 ampere hour battery, you can charge it to at about a 25 ampere hour rate. So it'll do okay. And some batteries, because of the way especially some of the sealed lead acid product, there's no such thing as a sealed lead acid battery. I don't care what they tell you, they're valve regulated. And I can go into a lot of story on that. But what happens is some of the batteries may self-regulate how fast they can charge, to where I put this voltage on it and that's all it will accept. It self-regulates. Other batteries may have to have external regulation. Batteries should be recharged, as soon as possible after they're discharged, or as soon as practical. Why? That's my backup power source, right? The event's over. I don't want to leave it sit, because what if another event happens 2 days from now and I wasn't going to recharge it for a week? Well, you have gotten caught in a very touchy situation, because you're not prepared now. Batteries should be stored, charged, and recharged while in storage. Again, I can plan for field day. I may not be able to plan for that ice storm because the weatherman, he was talking different from everybody else. 18 weathermen were making forecast, and one guy said, "You're going to have some ugly snow and stuff." And everybody, no, it's going to miss us. We're just going to see some rain. Well, the one out of 18 who happened to be right that time is the guy that's going to get you and all. That's not where you want to be and all. So, also, lead-acid batteries tend to degrade if they're not kept fully charged. So if you've got a lead-acid battery, the manufacturer on a new battery, again, I was working for a battery manufacturer. If we made a battery, we put it on the shelf day one. It's 6 months. If that battery was still on the shelf, we had to put it back on charge. Every 6 months. And this is a new battery in a good, clean storage environment. The battery's dirty. You get more self-discharge on it and all, so over the top of it. So you need to keep them charged. I would say nice thing would be once a month and all. This way, it's ready to go at any time. You can use a trickle charger or float charger. Utility companies, they've got batteries that are always on charge. They call them on float. So if something happens, that battery is at full capacity. So if they've got an 8-hour battery, that battery should go 8 hours. It's not 7 hours and 28 minutes or 7 hours and 49 minutes. It should go the full 8 hours because it's at a full state of charge. So, lots of different type chargers we can go out there and buy. You can go out and buy some inexpensive automotive chargers. They'll charge these lead acid batteries fine. They'll charge some of the lithiums, okay. They get filtered chargers. Well, a filtered charger now can start doing stuff with the battery because now that DC signal for a filtered charger is much smoother. So it's not going to be electrically as noisy. Most batteries don't have a problem with either of these. Power supply / battery chargers. Now we're getting into the units where I can use that battery while it's on the charger, but that power supply charger, it can also run other equipment at the same time. This is what utilities do. Because this substation down here, they need to trip a breaker. The battery provides the energy for tripping that breaker. Meanwhile, the power supply is keeping the battery fully charged and running all the other little instruments and stuff they need up until that breaker needed to trip. And then for a few seconds, they get power from the battery because that breaker's taking more energy than what the charger does. Then breaker's tripped and everything gets back to a normal state and it recharges the battery and keeps all these other loads happy. So that's what they do. The power supplies, be careful using a power supply to charge batteries. Some power supplies do not like a substantial energy storage device on the output. Could be a monster capacitor, could be a battery, but under the loss of AC, some of those circuits expect that energy to dissipate and go away. And if it stays there too long because I've got a battery or a big capacitor bank out there, it makes things die. My former employer knows about that because we have power supplies, we put diodes in, or we go hook up something and we put a diode external to the power supply to protect the power supply should there be a power failure. So, pulse chargers. For a while they were very popular. I'm not sure that they really brought anything to the table, but people liked them. They made claims about how great they were. I can't say that I saw any research papers that were definitive one way or the other on whether or not the pulse chargers really help that much. So that's some of the things they had. Going backwards. How large a charger do you need? About this tall, about this wide, about this deep ought to do it, right? Oh, that's not for your power plant, that's for your radio. Well, that same charger size would physically might be okay, but that's probably not the best way to try to go buy one or acquire one. How deeply is your battery discharged? How long do you have to recharge the battery? And do you have other loads you've got to support at the same time you're recharging it? We talked about it, this example, we were 96.6 ampere hours discharged from the battery. I'm going to take 2 days to recharge it. I took a day discharging it, so 2 days to discharge it's not bad. That's double the discharge time. A number of places, they figure they'll recharge it in 4 times the discharge period. I'm saying no other loads on the battery, but if I had other loads on the battery, I just add it into the current that the power supply / charger has to deliver. So the charger side, I take the ampere hours I need to recharge, I divide it by, I multiply that times 1.1. That's a recharge factor that's been used for lead acid batteries for years. It's actually probably closer to maybe 1.06 as with newer batteries. Industry has stayed with the 1.1 though. Why? It's close enough. Lithium batteries are probably more like 1.01, 1.02 for recharge efficiencies. So, makes a little bit of difference, but not a huge amount. I've got 48 hours, 2 days for recharging it, so I have to have 2.21 amperes out of that charger to recharge that battery in that amount of time. Very simple. So what sounded to be real black magic, it's actually pretty easy to calculate that. So, any questions thus far? I see some people taking notes, so I'm not going to try to rush you on it. What if I was operating the radio at this time? I was 23 amps. I'd take the 21.2 and add 23 amps to it, which would put me at 25.21 amps. That would power my radio and transmit at full power, plus be recharging my battery. What I haven't allowed for is, well, when I'm off key, like that 22-hour bit, 2 hours on, 22 off, roughly 10% duty cycle. Well, when I'm not transmitting, all 25 amps is available for the battery. So not 25 actually, because we said their standby current was 2.3 amps. So I've got 22.7 amps available that the transmitter doesn't need that I can now put in the battery. So if I added 25 amp charger would do the job with the duty cycle that I'm using. You don't have to, and I mentioned the 96.6 times 1.1. Well, if I used 1.0, that would drop to basically 2 amps, or just a touch over 2 amps. 0.2 of an amps, and that is not that big a deal for the level we're working. But if you want to get real precise with a different battery, just use a different recharge efficiency. Any questions? Are you hopelessly lost? Okay. Let's talk a little bit about the different battery types. I'm going to try not to run too long. We got started a little late, so I'm going to run just a couple of minutes over. Standby batteries. I'll give kudos to C&D Batteries, C&D Technologies. That they provided the pictures that I'm using for this. Standby types basically are designed to sit on a float voltage to be maintained at a full charge all the time. There are also other batteries that are designed a little bit differently and intended for cycling. Car batteries, forklifts, electric forklifts, they're popular. No fumes and all, so they like to use those in warehouses and factories. Solar batteries. I don't live in some place where the sun shines 24/7, so if I have a plant with solar batteries, they get charged during the day, they're going to be discharged at night. So that's a cycling battery. Deep discharge batteries. Anybody that likes to go fishing and it has a trolling motor, you've got a deep cycle battery on that, I bet. Otherwise, that battery probably doesn't last real long because that battery doesn't like being cycled, because some of these bass fishermen, they go out before the sun sets, before the sun rises, and they don't come back in until after the sun sets, and they spend a whole lot of time not with the big motor they use to get to that fishing hole, but with the little trolling motor moving around that fishing hole. So, there's two types of battery technologies within the lead acid. We have the VLA, which is a vented lead acid. It also gets called flooded and all. It's basically, it's filled with sulfuric acid. They're also called wet. They have lead calcium, lead antimony, lead selenium, and pure lead batteries. So there's 4 variants. There's slight difference. I'm not going to try to address characteristic differences in here tonight. We have the VLRA, valve regulated lead acid, also called maintenance free. These batteries have a valve, a little pressure relief valve in them, but you don't ever put water in them. Hence, they're considered sealed. You never add water. AGM, absorbed glass mat, that's what's the most popular right now for a lot of your battery technologies. But you have spiral wound, which Optima battery uses, and Optima makes some good batteries. There's some electric drag racers using those spiral wound batteries because of the performance. You know, I need a whole lot out of that battery, and I need it for a very short distance, about a quarter mile or so. And they've had those batteries explode because they just abuse them tremendously and all. But there's also some hybrid, and there's some funny things people are doing, the combination to get certain characteristics. And those tend to be very proprietary for manufacturers. Very few batteries are pure lead. Lead antimony was a great battery, but it tends to use a lot more water than a lead calcium. Before the 50s, it was the battery technology and all. And you still see it today. A lot of forklifts still use lead antimony type batteries. If I go buy a new battery for my forklift, it may well be a lead antimony because it cycles very well. The lead calcium, it works real good in standby operations, uses about 1/10 the water that a lead antimony, meaning lower maintenance. So that has made it become very popular and all. You have the charge current. When it's fully charged, it has a little trickle current. It's a lot lower with the lead calcium than it is with the lead antimony, which was another thing people are looking at. When I've got this battery, if it works the way I want to, over a 20-year life of the battery, I'll use it about 20 hours maybe. But the rest of the time, it just sits there on float. So over 20 hours, the cost of energy to maintain that battery adds up. And so a lot of places use that. Lead selenium, it's very similar to lead antimony. There are a few people still using it. I don't know of any manufacturer in this country making them. There's still a few made over in Europe, and some places still love them, and they specify them, but it's still in use. Lead's a hazardous material. You don't like it free in the environment. That's why that's why we've gotten rid of lead pipes, or trying to, for water pipes. That's why plumbers can't buy lead solder in general anymore, because it's deemed not to be nice. Batteries contain acid. I mentioned the lead acid batteries. I mentioned that a little earlier. That sulfuric acid in it, well, that's a nasty corrosive and all. Although you can get it on you and it won't hurt, but if you got a cut, you're going to know it. It stings mighty bad. I speak from experience. They are a substantial voltage or a substantial energy source. I speak from experience. I jump-started somebody's car and I got the polarity reversed. I bought a new battery that afternoon. After I ran in and washed the acid and all that had gotten on me. It's a whole lot of uncontrolled energy released. It literally blew the top off the battery. So I recommend not doing that. Batteries generate hydrogen and oxygen gases. When they're early in the charge, they don't, but as you finish charging, then they enter a gassing phase, and basically the water's breaking down into oxygen and hydrogen, and it escapes. These standby batteries we showed earlier, a number of them have a flame arrestor. So if something happens outside, it doesn't get inside and make the cell blow up. So a lot of places, they require ventilation of big battery rooms. I have been in a battery room that makes this room look small. There were hundreds of batteries, cells in there for a big installation. They have special ventilation to make sure they don't build up an explosive concentration of gases. Batteries are heavy. I don't go out weightlifting, but moving batteries are heavy. When, they get big, they get heavy. I mean, your car battery is going to be on the order of 50 pounds. A 100 ampere hour deep discharge battery for your trolling motor is roughly 100 pounds. They get heavy in a hurry. So there are a number of drawbacks to hazards, because that can be a hazard to your back if you don't pick it up right, or your toe if you drop it, or foot. So there are a lot of indirect hazards that you can have because of the weight. I'm going to go into a little bit about lithium battery. I'm going to try to talk a little faster since we've almost used our hour. The lead acid battery was invented in 1860. It is not a new development. Internal combustion engine was invented in 1872. I said invented, I didn't say it entered practical use and all. First commercial gas-powered automobile, Kokomo, Indiana, in 1894. So it took a little while even to get into use. And the Pioneer, I think you find that type of information only from somebody researching history, because that brand has been gone for so long, nobody even remembers it ever existed in general. Lithium-ion battery invented in 1985. The lithium iron phosphate battery, 1996. We're talking over a century after lead acid. Lead acid is a very mature technology. The lithium battery technology is much newer and all. Honda launched the EV Plus, which was a lead acid battery, in 1997. People were playing with other electric cars in the 80s, but they never could make them go successfully because of the batteries. First lithium-ion battery laptops about 1998. Why? Because it had better energy storage density and all than some of the other technologies for batteries they were trying to use in them. The iPhone launched in 2007. Doesn't seem like it's that long, but it had lithium-ion battery in it. Tesla Roadster 2008. I didn't say it was widespread, but that's when they had it. Again, lithium battery technology. Green Cube, who's a company that helped provided a lot of this information, Green Cubes, they built their first lithium-based battery for a forklift in 13. So they're barely 10 years old. Nobel Prize in Chemistry for lithium-ion invention in 19. It takes a while before people can see, is this invention really important? It has proven to be, and so a Nobel Prize was awarded in 19 for that. So that's a quick little bit of history, some various interesting pictures maybe. One of the differences with lead acid and lithium, the red curve in the top graph, lithium, that's the voltage. It is pretty flat, which has some benefits, and it also, if you're working on making battery chargers, it's a pain because I can't measure the voltage and easily tell what that voltage is, what the state of charge is. Lead acid battery curve in the blue, it drops off pretty much. So if you look at that 11.73 volts we were looking at, we hit that somewhere between 50 and 60% of the lead acid battery capacity. We don't catch that on the lithium till we're up about 95%. So by changing battery technology, I can get a lot more usable energy from my battery. So that's why it's important. I mentioned about knowing what your battery, how your load responded. Maybe your load doesn't care, but if your load does, that might be a good reason right there to go to lithium ion or lithium iron phosphate instead of going to the lead acid. The lithium battery voltage is pretty constant regardless of discharge rates, where the lead acid on these red curves, it can change drastically according to how heavy you load that battery. There are a lot of battery design decisions that go into lead acid according to, do I need a battery that's going to be discharged in 15 minutes for an uninterruptible power system? Or do I need a battery that I'm going to run 20 hours? Because they do things to help get better performance depending upon the application. There's several lithium-ion chemistries out there. To the left, the lithium iron phosphate. That's what you buy for the better batteries. The ones that we see people out here selling, that's what they're going to have. Over here on the right, these are your they get referred to as pouch batteries. That's what's in your cell phones, your tablets, your laptops. They're a little bit better for some applications, but other applications, they're not necessarily as good. So that's a lithium nickel manganese cobalt battery. So they do some crazy chemistry stuff with it. Does it work? Absolutely. You get laptops now that'll run 6 hours, 8 hours for watching movies, which is great if you're flying long distance. Open your laptop and watch a movie. Watch another movie because you don't like anything that the airplane has on the air entertainment system. But over here on the left is the batteries that we really are better interested in. Battery management systems. I'm going to very briefly talk about it. Basically, lead acid batteries, could use them. It's just they're more forgiving. And if I overcharge a lead acid battery, it gases. So it uses up a little water, it evaporates out, whoopee-doo, no problem. Not the case with lithium ion. They get very unhappy if they're overcharged or undercharged. So we have a battery management system to help with that. If I have a battery like a 12-volt battery, typically doesn't have a battery management system in it. It's only 4 cells in series. There are bigger battery packs out there. I've got a forklift. Okay, it's got a lithium battery in it. Okay, that's an 80-volt battery. Okay, how many cells are in series? I don't know. It's about 3 volts per cell and 80 cells, so it's probably about 25 cells in series. I need to make sure I keep the charge on all those cells balanced. So I have a battery management system to do that. And all. Where lead acid, I'd let battery gas, some of the cells gassed a little bit, no big deal. I add water and I'm done. The lithium batteries don't like that, so the battery management system, usually the battery manufacturer has a package that has that in it if it's needed. For the 12-volt stuff that we use, they typically don't put them in because all the cells are manufactured at the same time and they're so closely matched because they're in the same manufacturing lot at the same time and all, it works fine. But it could be a problem if instead of working with 4 cells, I'm working with 40 cells. Because if I'm an electric utility, I have 60 cell lead acid, which is about 120 volts, so I need about, 40 cells of lithium to give me that same type of property, maybe 38, but a lot of difference. Let's see. Well, I think that's probably it for my stuff. I have talked for nearly an hour, almost nonstop. Do I have any questions that I can answer? I know you got a lot of questions that I can't, so.
Do power plants use battery backup? Or?
Yes. The lead acid battery stuff that I showed at the first shot where they stand by, there has a big rack. You will find those in electric power generating stations. You will find battery systems like that in large switching plants, chemical plants. A few years ago, I was down in Texas, Freeport. Had to go visit a customer down there. The unit that I needed to go down to see, I needed to be in front of the unit about 2 hours. I spent about 3 hours in training so I could spend that 2 hours because of the hazards of the chemical plant. Complete with my respirator and where I was to run to. There's another phrase I could use to describe it because I need to get there very quickly should the alarm go off. But they have chemical plants, a lot of petroleum type plants. And when I say chemical, I'm thinking we could be talking oil refineries, we could be talking fertilizer factories, we could be talking anything where loss of power could cause a major problem. And when I say major problem, I'm not talking about, we got this little problem because I've got this chemical that polymerizes and it's going to, go from liquid to solid and it's going to cause this pump. No, I'm talking about much nasty materials. I was in a plant that actually made chlorine. We had a respirator unit that we wore on our belt. I had to have training, and you had to be trained on what to do and all. And we had 2 battery chargers. I was working on the charger stuff, and the 2 chargers we had, they had a big question about one of them, and we had to make an adjustment. But it was, again, about 3 hours of training for less than 2 hours in front of the unit because of the hazards. And that's a hazard. That's just to get you out of the plant safely. That doesn't count the surrounding area. But a lot of places, Chickamauga Dam, TVA's operation, they've got the switchyard, their batteries to support that. Inside the building in the water turbine area for the generators, a lot of the controls, their battery backup on that. Because if something goes wrong, I don't want something shorts. Well, that was my power source to run everything. That's not a good situation because now I can't operate my protection equipment. So, yes, there are a lot of places have batteries. Your old telephone offices have batteries. Cell sites, a lot of times they'll have anywhere from 3 to 5 to 8 to 24 hours of battery. I have been to one place that had a little over 24 hours of battery in Northern California. It's a microwave relay. It was only 45 minutes once we were in the snowcat to get to the site. That site goes down, they got to get a technician up there. And they've got several propane tanks filled. They're filled before they get the first snow so that they can operate regardless. Excuse me. Any other questions?
We certainly appreciate your knowledge.
Oh,
You've educated us all here on what you know.
well, you had a question, ma'am?
You said that battery's considered to be end of life if it reaches 80% of its original capacity. Is that why simply safety or?
That is actually in the IEEE standards for stationary batteries.
Yeah, but why that number?
That number has evolved over decades. What happens is, a lead acid battery starts aging the day they make it. It loses a little bit of capacity over time. So, at what point do I say that it's worn out? 5%, 10%, 50%? So, by consensus, they've had people with many different backgrounds involved with it, not only battery manufacturers, but also battery users. Okay, how long can I run this battery? How much overrated do I need to have this battery to get a life, to determine my service life? Now, does that mean when that battery hits 80% that it'll quit? No. What it means is I can probably run that battery, down to 40% maybe. How many times have you gone out and somebody's had a car and it goes ronk, ronk, ronk in weather like this and then it catches? That battery is way past end of life, I would say, but it's end of life as defined by the standards. It's not end of life because whoever's got that vehicle, they're still using it, so it's still being used, but it's past its designed service life. So it's really not that it will just stop working. They've looked at what the requirements are, so they have a uniform measurement for everybody. So when I put in this, let's say this was some critical load for something in a hospital or something, how much should I oversize my battery to do what I need to do? So I make it so that it'll 80% of the battery capacity, so I've got years of operation until it has worn out and I need to replace it. And all. This way, everybody's using the same measuring stick. Because as we have gone out, and if you bought anything online, you probably discovered some vendors are not quite as trustworthy as you would like. Well, those same types of people will try to sell product of some kind, especially if they can make money at it. So they'll kind of fudge numbers and cheat a little bit. So this was really done to try to make the field a little bit more level for everybody. But that was a number, it was determined by the IEEE over years and has become and is an accepted international standard. Any other questions? I don't know if the concession's still open for dinner, so I can't help you on that one. Guys, thank you. If you've got any more questions, you can find me online with my call sign, ky4fh@arrl.net. You can email me. That is ky4fh, Kilo Yankee 4 Foxtrot Hotel @arrl.net. And all. Thank you. And I'll be around to answer a few more questions and all too. And also thank North Georgia GMRS for their support in recording this, and hopefully it'll be something worthwhile for their people. Guys, do have a good evening, and thank you.